I would like to welcome everyone to our construction-focused presentation, Constructability of Passive House. Organized by New Passive House and presented by Monadnock Construction. I would like to thank Monadnock for your support of New Passive House throughout the years as a sponsor, and we are very excited to have Monadnock present today's multiple large Passive House projects. It is my pleasure to introduce Amy Fowler, who is a New York Passive House member and will introduce today's Monadnock team.
Passive House construction details. So we have here to present Joe Styla. He's a project manager at Monadnock. He was involved at the Morris 2 project in 1240 Metcalf Avenue. And then we have Tom Barker. He's the MEP project manager at Monadnock. He worked on Cornell and 425 Grand Concourse as well as Betances. And Harry Priya Aluminali, project manager. She was involved in Cornell, Morris 2, and the pre-construction phase of 425 Grand Concourse as well. So with that, I will hand it over.
Hi, everybody. My name is Joe from Monadnock. Thank you, Amy, for the introduction. We're going to be discussing constructability of passive house. On the first slide, you will see 5 passive house buildings that have been completed or under construction right now. The one to the top left is Cornell Tech, which is a building on Roosevelt Island. The one to the top right is Morris 2 Apartments, which is in the Bronx on Morrison Park Avenue. The one to the bottom left is 425 Grand Concourse. In the middle, we have Betances, and on the bottom right, you have 1240 Metcalf, which is in the Bronx as well. These are the 5 passive house principles that we'll be discussing along our slides today. Thermal insulation. So some of you may know passive house requires a substantial amount of insulation. It starts from the bottom up. Pile caps, grade beams, and bottom of slabs are required to be insulated with a higher thickness versus conventional construction and in more stringent tightness between installation. The insulation product data has to be moisture resistant, which is typically XPS. And also something to keep in mind for is the excavation amount. It has to be excavated for pile caps and depths or widths for the formwork have to allow for the insulation as well, which a lot of times contractors forget. And many times we've had pile caps or grade beams excavated only to the width and the depth that's on the structural drawings, not accounting for the 4 inches of insulation on the exterior or on the bottom, and we had to take the rebar out and excavate deeper and redo the formwork and rebar, a couple days before the pour. It's something that people take lightly, but it does happen a lot in the field as a common mistake. On the right, you're going to see some details that we drafted with an architect for the Morris 2 project, just to explain the extent of the insulation for the contractor, how there has to be overlap, the 12-inch minimum overlap on the bottom of the footing, the insulation on the bottom of the grade beams, and how there is no insulation underneath the pile caps. Masonry Wall construction in passive house. So the project I'm working on right now is I believe is the largest multifamily first block and plank passive house building in, I believe, in New York City, which had some different cases that we had to learn. Large cavity for one. We had 4 inches of insulation in the cavity with a 1-inch airspace. So the dimension from the face of the block to the brick was 8 5/8. The reason we worked with the architect to use a mineral wool is because it allows for constructability and workability ease for the masons to pack around the different steel angles, masonry ties properly, get in behind those ferroclip brackets, and allow for the plumbous deviations on the masonry wall construction. These are some photos you see. On the top left was a QA/QC mock-up that we did with the contractor and the consultants on the job for Metcalf, just to work out the sequencing and the insulation and proper installation requirements as per manufacturer specs. So we would do every step we had the manufacturers come out and verify the thickness of it. We would have the consultants come out and verify the placement is correct. We would document photos throughout every step and use it as a reference throughout construction. In the middle, you're going to see the opposite of mineral wool. It's an XPS insulation within the cavity, which I said is not preferred because it's more rigid and you have to work around fixed items like block, steel, and you can't get in behind those ferrule brackets properly, which you'll see on the top right. And then on the bottom right, you're going to see the 2 layers of mineral wool insulation below the sill on top of the brick shelf. Now I want to discuss the ferrule brackets on the top right. Ferrule brackets have benefits to passive house construction because it allows for the insulation to get packed behind the angle versus where you have a traditional relieving angle like a bent plate or a 6x6 angle. You lose the R value throughout that whole length of the wall or that angle. So if it's a 6-foot angle, you're losing R value for a 6-foot by that half-inch thick steel with no thermal break. Ferrule also has thermal models that the passive house consultant can use to input into their thermal modeling. The next slide is just showing you a detail of an EFIS job that we did in the Bronx. It actually had a block and brick first floor, and then the second floor to the 15th floor was an EFIS application by Drive-It. It was a 7-inch EFIS on this job, and because it was so thick, we had to reach out to Drive-It to confirm that 7 inches could be applied in a single thickness versus 2-layer application, and they did confirm that it could be applied in 1 layer. And on the bottom, you see some of those details for the foundation overlap. The 4 inches of insulation around the brick shelf, the aerated block as a starter course for the brick. So the R value is always continuous all the way to the bottom. This slide is explaining panel conditions. So on the Metcalf project, the architect wanted to have these metal panel accents on the sill of the window, the jambs of the window, and originally the head of the window. We had to work out a detail to properly support the jam fin without anchoring to the window frame, without anchoring to the brick because it wouldn't structurally accept it, and without damaging the air barrier blindly after the masonry was done. So what we worked out was we would install the item you see in green, which we refer to in this text as a ground, which is a 16 gauge galvanized steel angle that is thermally broken on the block. The panel contractor would supply this thermally broken shim and the angle to be installed in the cavity by the mason before the brick was installed. And before the brick was installed, the mason would seal all the anchors and the back of the angle to the block substrate and that 1/8 of an inch or 1/4 inch gap with the Henry liquid sealant. After the masonry was completed, we would wash down the wall, and the panel contractor would come in, screw the first piece in between the window frame, between the edge of the window frame and the inside of the metal in that 1/2 inch joint, and then he will also screw on the outside against the brick in that 1/2 inch caulk joint, which will not disturb the metal on the inside at all. Different roof conditions. Passive house requires usually an average, depending on the size of the building, can vary anywhere from an R36, I think, to an R50 roof. On Metcalf, we have an average of an R50 roof, which roughly will allow for 12 to 13 inches of insulation. In that, you have to coordinate the brick and the block height for the top of parapet, for coursing and proper clearances. I think you have to maintain a minimum of 3'6" above the finished roof. So a lot of times you don't realize when you have the tapered insulation, you might end up at 14 inches based on the pitch and the length at the parapets or at the bulkheads. So you have to have a proper step out. So just coordinating all those transitions early on is key. Verify insulation requirements at the drains. Some jobs have Irma roofs, conventional roofs, so you have to look at the details of the drains. Are the drains up high to the top of the insulation, or the drains sump down? Sometimes the architects show them up high, and we like to sump them down because of the different body connections between different drain manufacturers. So verifying that is correct is huge. Verifying proper clearance to work and tests for compatibility between thermal blocks under any Dunnage or equipment. So a lot of times we set these large Dunnages that are supporting these ERVs or VRF condensers on the roof early on, and we have to thermally broke them to the roof slab. So you have to the roofer will have to work underneath these underneath the equipment in the dunnage while he's doing his roofing. So you want to make sure that those dunnages are up high enough where he can work under that properly and reach in, 5 to 8 feet. So we like to maintain a 3-foot clear from the underside of the dunnage to the top of the roof. Out of sequence waterproofing of thermal blocks during temporary construction. As you're going to see on the top right, the red line around the thermal block has to be sealed during construction, so we'll temporary roof that in so we don't take water in there during construction until the permanent roof is encapsulated later on, which is shown in blue on the top. Also, you're going to see a detail of blocking on a low parapet. Because it has insulation on the top of it, we cast in these anchor bolts, which the mason will grout into the top course of block. We keep the bolt up high enough so we can account for the 2 layers of plywood and 4 inches of insulation. So usually it's up 6 inches, and then they'll drill out the wood on top and put in a nut on the top to secure it properly instead of drilling through blindly later on. And the detail on the right is a high parapet, which does not have insulation on the top of it because it's above the 36-inch thermal transmission requirement. This is just 2 photos from roof conditions. The photo to the left is showing Irma roof, which is 10 inches of insulation. It's 2 layers of 2-inch XPS and 2 layers of 3-inch XPS, which equates to R50. This roof had to be dropped 15.5 inches from the top of the roof slab to allow for this insulation buildup with the pavers and the pedestals plus the insulation, which structurally on a plank job was not easy to accomplish. So that's something you have to keep in mind. And the image to the right is just showing you what I was talking about, the insulation buildup and trying to work around this equipment dunnage after the fact that it's installed. Thermal bridge-free details. The image to the top left was from the Cornell project. It was a generator dunnage. You can see that we have a thermal block underneath the column installed to the roof slab, and there's a zoom in on the top right. So they set the thermal block. The thermal block comes pre-drilled. We land the column on it, and they bolt it into the slab. And then they'll pack it with non-string grout because the slab will have a little bit of a taper to it, so it's structurally sound. The photo to the left, to the right of the table on the bottom, is a thermal block that's built into a masonry wall, which is used for a unitized ERV discharge so that the ductwork does not come in contact with the CMU, and that the masons don't try to have to split a block around the duct, which would prevent a improper detail for air sealing around it in construction. And it also prevents condensation between the metal and the block. The image to the right is a insulated roof curb. This is just a sheet on thermal breaks. On the top left is just a structural data chart on the product shown below in the 2 photos. That was the thermal break that we used for the relieving angles at the Metcalf project, which the engineer has to review for the moment load on the brick on the angle to make sure it can withstand the load. The image to the top, the right of the chart on top, is a snapshot of a shop drawing from the manufacturer showing the size of the thermal block, the size of the hole and location of the hole, which the GC has to approve prior to release. Just to give you an idea, those thermal blocks will take 3 to 4 weeks in shipping and manufacturing to get to the job, so you have to release them early. The photo to the right is showing a panel detail with a connection and a thermal break. The chart on the bottom is showing different methods of anchoring the insulation to the backup wall. Traditional conventional methods use stick pins, and we found this product called Ramset, which has a plastic shield. When you shoot into the insulation, it mounts to the wall with a plastic shield and has a middle pin, and it has a chart which provides thermal values. You'll see the reduction from a stick pin to a Ramset.
All right, I'm going to take over from Joe at this point. Thank you, Joe. Air tightness install details, a 3rd mantra with Passive House. And I'm probably not going to dwell too long on this section because Joe kind of covered a lot of this as he was going through the installation install details and the mock-up install. What I would like to emphasize is really the difference between, I guess I would say, conventional projects and passive house projects. It's critical on every job to make sure that the AVB is, there's proper coverage, there's proper transitions, compatibility between the different membranes. That's applicable for any project. If anything, on passive house, the emphasis becomes a little bit more because you actually quantify all of this at the end of the job by means of a final blower door test that you have to pass in order to be called a passive house project. And obviously this means that there's a lot of inspections that happen and there's a lot of eyes looking throughout the project. And typically, we have our contractor, meaning subcontractor, do their inspections. Monadnock as a CM or GC, depending on who we are on the job. We have our field personnel and sometimes dedicated facade field personnel who are looking at the facade work and the quality of installation on a daily basis. And in addition to this, there's a third-party inspector, the special inspector who, the TR sign-off entity who's looking at the facade. There is a facade consultant on most of these jobs who is, verifying that the installation is okay. The architect during their weekly visits, there is the passive house consultant. So with all these eyes looking at the job, it's really the difference is more inspections and more coordination that has to happen. And one thing I would like to say is something that's different in terms of air tightness details is the photo that's shown at the bottom, which is an interior wall in the building. And this is actually from a trash room, trash chute wall. And most of the architects and the consultants in the room probably have already gone through this, where, we're talking about making the building airtight and conditioning the space inside the room, or not introducing unconditioned air, I should say, into the building. But meanwhile, you have a trash chute that typically is open to the atmosphere, and it's generally leaky. You have a laundry room where you have makeup air that's usually unconditioned, introduced for the dryers. And one way to combat all this is we've sealed these rooms to exclude these as part of the envelope. The rooms are generally closed. It minimizes the air leakage into the rest of the building. It helps with not just for the passive house test, but in general makes the building itself more airtight. And recently, and Joe probably has more insight onto this, we've also explored aero sealing for the trash chute risers to make the chute itself a little bit more tight in any way that we can. And obviously, all of this is ultimately to pass the final blower door test. And usually the final blower door test is done at the very end of the job when the building's ready for occupancy and TCO, and all of the finishes are in, and there's really no way to, if for any reason there's a leak happening, there's really no way to identify, or no good way to identify where the leak is happening. So there's a lot of intermediate inspections that can be done and tests that can be done to verify that we are on the right track to get to the final blower door test passing requirements. We've done performance mock-ups on many projects where the window gets tested or the wall assembly of the windows getting tested. There's the guarded blower door test that can be done. And probably most of you already know about it, but I'll quickly skim over this in case someone doesn't. Typically, guarded blower door test, you pick an area of test. Sometimes it's a whole floor, and you pick a floor above and a floor below. If you're testing an apartment, you pick the apartment adjacent to the tested apartment as part of the test, and all 3 floors would get pressurized or depressurized, which goes into both of the cycles. And this helps you identify if any leakage is happening at the floor that's actually being tested. Where this becomes critical is the timing of all this, because the guarded blower door test is something you would want to do when you are early on in the construction and finishes are not really in, and you have a way of identifying where the leak is happening if you're not meeting the required performance values. So this means that the hoist is probably installed and you have a hoist run. So the exterior skin is not entirely completed. You may have apartment panels not installed, electric meter banks not completed, the elevator shaft would be open. So with all these items, it becomes difficult to really quantify how much of this leakage is truly from the exterior wall versus interior leaks that are really leaks only because you're mid-construction. So, and obviously there's ways around it. It's just a little bit of time and effort that has to be put in terms of, sealing the panels, sealing the hoist run and all this, and making sure that the trades are not on the job when this is happening, because this is going to obviously interfere with work and the schedule of the job. And we've attempted to do this on other projects. It's been with success, it's been without success, but either way, you know, the guarded blower door test is, it's just a way of trying to see if you're going to hit the final blower door, and there's no guarantee that, you know, you're actually going to pass the final blower door just because a guarded blower door went, because you could have fake results too with all this, you know, sealing that you're doing, that's really not applicable for the permanent condition. Windows and storefront. This may be a very important criteria for passive house as from a design perspective, not so much from a construction perspective, but I think it is a very relevant factor from cost, lead time, if you were to consider. So passive house, and again, between the different projects and between PHI and FIRS, we've seen different U value requirements depending upon the size of the building. The smaller the building, the requirements become more stringent compared to the larger buildings that have higher heat loads and you have less stringent requirements. So we've had projects where we've had to go with double pane windows that meet requirements versus some projects where triple pane is required. And obviously at this point, there's also this comparison of aluminum windows versus thermally broken aluminum windows versus UPVC windows. What makes more sense in terms of cost for the project, in terms of meeting the performance criteria? So this is more of a design item. I don't want to dwell on this too much from a constructability perspective. Where it may be effects from in the field is maybe, you know, for example, the triple pane glass is a heavier window compared to a double pane window. And that makes it, you know, workability wise harder in the field and adding cost to the job. The storefront is a more of a touchy subject though, because, and it really comes down to cost, lead times, because there are fiberglass storefronts that are available. There are UPVC storefronts, but there's really no good storefront system that's locally available that can meet ADA requirements and be capable of being integrated with all the hardware security configurations that are required for the project. But I should say that the storefront manufacturers, you know, like Conier, YKK, Oldcastle, they are a lot better than they used to be. They have thermally broken systems, and I try to share some photos of that I found of the performance, I guess, the thermal imaging analysis that they have shared for their doors as well as the frame. And they do have the thermally broken systems with superior, relatively superior performance, even though it may not be meeting the same requirements that are set for the windows. The storefronts have been proven to be working as per the energy model so far.
Hi, everybody, Tom Barker with Monadnock, MEP PM. So a lot of times we do get involved in the value engineering and constructability phase with the design team, and our passive house jobs accomplish ventilation with ERVs and the heating and cooling with VRF systems. So we'll dive into a couple of these subsystems, and basically we're only talking about multi-story passive house buildings. For the unitized, so one type system is a unitized system. Basically, it has a dedicated unit in each apartment. Like you can see the layout on the picture on the right. The picture on the left is the actual unit. And the picture to the lower right is actually the penetration through the facade that Joe was talking about earlier. And basically the entire system, including its outside air, exhaust, supply, and return, are all within the apartment. And as you can see from that picture, one of the big impacts to passive house is that you're actually penetrating the facade. So now you have a facade penetration in every apartment, 2 facade penetrations in every apartment. And basically that's another potential point for failure for your air sealing, and another point for quality control. And another thing to consider as well is on a typical apartment, when apartments are stacked, typically you also have to consider the separation between the exhaust and the supply air. You know, if a lot of times these floor to floor, you're not more than 10 feet apart, and you have to kind of you know, alternate between supply side and exhaust side, so you can get that separation from the floor above, if that makes sense to you. So there's a lot of other considerations with the unitized system. You're going to need your own dedicated closet for it. And obviously I'm saying this all relative to a centralized system, which we'll get into next, but you'll need your own dedicated closet. You'll need your own dedicated, you'll need a dedicated circuit to that unit. You know, you'll need a separate condensation riser. A lot of times the condensate comes out low from the unit, so it's not really feasible to come across the room or come across a wall to connect to a nearby condensate riser for your VRF system, which we'll get into later. And also, you know, the blocking condition that we used for this exterior penetration, that blocking made for a really good substrate for, you know, using a piece of neoprene or something like that to basically get that air seal at the penetration. So this is the centralized system. It's a lot cleaner for us installation wise. I feel it's a lot easier in general coordination wise. A little bit more complicated on the crossover floors because obviously now you have a dedicated space in each apartment for a riser, but you eliminated the separate condensate riser, the electrical points, the dedicated closet. Of course, you do need the floor space for the risers. There is a little more in the system as far as fire smoke dampers when you come out of the shaft, or 2-hour rating when you come out of the shaft. But in general, this is it's a much cleaner system for us passive house wise, because you're really only dealing with the air sealing of the duct, and which we'll get into later, and also the penetration through the roof. So here's our rooftop unit from Cornell. This was a bottom outlet rooftop unit. So you can see in the pictures, we have the thermal blocking underneath the curb, and then you can see in that picture to the lower left that we have the extruded polystyrene that we insulated the interior of the curb with. This is kind of it's not really a seamless detail, and it's kind of messy, and I'm not really a big fan of these bottom outlet units on a passive house job. Like, just because once it's set, it's basically set in place, and you're not really going back to that area after the fact. So comparing that to a Dunnage mounted rooftop unit on the next page, where we actually utilize a side outlet ERV. This is a lot cleaner for me. The Dunnage, with the Dunnage, you only have the Dunnage that's connecting to the roof, so you only need the thermal isolation block there. And then obviously where the roof curb penetrates, you'll also need the thermal blocking under there. And to me, this is a better long-term solution. Also, if that unit ever got changed out or needed to get serviced or replaced, it's pretty easy to not only get the unit on and off, but basically reconfigure the system for a new unit. Before on the rooftop, on the bottom outlet unit, the new unit would basically have to fit or match that duct configuration. And with the side outlet, you can run out your duct and eventually match it to the risers. Like I said before, we do our VRF systems are ubiquitous in passive house jobs. All of our passive jobs, the heating and cooling is done, residential heating and cooling is done with variable refrigerant flow systems. And those systems can either be with or without heat recovery. So, and the configurations that we generally consider all involve like an air-cooled condensing unit that's serving multiple apartment units. So we don't have any one-to-one ACU to apartment setups. The single mode system, what I mean by that is just the unit is either in heating or cooling. And you can see on the pictures to the right, this is Cornell, and we had a dedicated ACCU on every floor that fed 2 floors on the south side, and then on the next floor we would have an ACCU that fed 2 floors on the north side. And the way we did this was we ran a refrigerant header around the perimeter of the building, either south or north, depending on what ACCU was. And then we would stub up to the floor-mounted fan coil unit that was along the perimeter of the building. And this is it's a pretty simple system. There's a lot, it's not a lot of piping. You're basically using one header, and there's a takeoff from every header to distribute to the fan coil unit. One of the complications at Cornell was since we had that horizontal penetration to the condensing unit, the condensing unit was in a pseudo exterior space. So all of those penetrations needed to be air sealed. So that was another situation where we had we had a typical condition at every floor that was, something that also needs to be QA QC'd. We've done at Betances, we have a single mode system as well, and we distribute that vertically down the shaft with the duct risers, and then we branch off of those risers to feed the units. One big drawback with the system is, two big drawbacks with the system is, tenant comfort on the shoulder seasons. Sometimes, because you're only operating in one mode, some tenants, obviously different people have different comfort levels. So you might get some complaints from people in the fall season that either they're too hot or too cold, for example. So with the heat recovery system, oh, sorry, I forgot to mention one other thing about the single mode. So the other problem with the single mode too is if you ever have a refrigerant leak or you need to service or take out a unit completely, once you cut into that refrigerant piping, you're basically compromising everything that's connected to that particular ACCU. So once you break that refrigerant piping open, all that refrigerant has to be recaptured and refilled. So everybody that was on that system would be down in such a situation. All right, with the heat recovery, only difference with the heat recovery for us is, we're adding a branch controller that has to be centrally located so that it can distribute to an apartment. Generally, that's how we do a home run to each apartment. All of those home runs can be isolated, and all of those apartments can be, like one apartment can be heating while another apartment can be cooling. And you could even go further and do home runs to each individual fan coil unit. But that really brings in a lot of horizontal piping and really complicates coordination. And in general, in an apartment, you're either going to be in heating and cooling. So coordination is a little more difficult because you do have like in our case at Cornell, we have vertical refrigerant risers that stub down and they penetrate out of the shaft to feed the branch controller and then distribute horizontally there. So we have a little bit of coordination with both vertical and horizontal refrigerant piping. And the horizontal, crossing the corridors, you have to fire rate that. You have to consider all of those things during coordination. And obviously with the thickness of coordination, with the thickness of the insulation on these pipes, you're dealing with 3-inch pipes for every one, even though the lines are rather small themselves. But with the insulation, it actually takes up a lot of space coordination wise. But overall, you're not going to get the tenant complaints or you're not going to have those system shutdown problems that you would with a single mode system. With our penetrations for the refrigerant, so what we typically do is obviously these penetrations is another source of air penetrating the building. So we have to make sure that obviously we seal around the refrigerant pipe as it penetrates the roof, and we do this by using an insulated prefabricated vault. And with that vault, we cut out those holes for the refrigerant, and then we use what's shown in the upper right hand corner, what's called an exit seal. Basically, there's a seal on the inside and the exterior of the vault, and that gets screwed down and it sandwiches between the wall of the interior and exterior wall of the vault, and also hugs the pipe. So it maintains that air seal. You can't always use the prefabricated vault because sometimes you're dealing with some field or design, not necessarily design conditions, but coordination conditions, that we have to work through. And for example, the trash chute is a really great place for the vertical risers to run up. And it's a great place to have the branch controller to do your distribution. But one of the problems is when it penetrates the roof, now the refrigerant risers are rather close to the trash chute. So it's not really feasible to do the prefabricated vault with the trash chute curb. So, the picture that we're showing here, those refrigerant pipes are about a foot away from the trash chute riser. So there's not enough to build a curb around the trash chute and the curb around the refrigerant and do the flashing. It's just not feasible. So what we decided to do was do a bi-level combined roof curb with a middle partition that you can see on the next page. And basically all we're doing here is we have two separate caps, one for the refrigerant piping, and that cap basically, that's shown in green here, and that kind of slides up and underneath the cap for the trash chute, so that we maintain our, roofing condition. It makes the roofing condition, obviously it makes it feasible to do the roofing on this curb. We have to make sure that our ducts are really tight for installation. We have to meet certain CFMs, and the unit has to operate within a certain efficiency. For example, a lot of time on my project at 425 Grand Concourse, we have to meet a 0.765 watts per CFM power consumption from the unit, which means that what the unit is designed to deliver has to be delivered, and that means we need tight ductwork so we're not spilling air where it's not supposed to go. So there's an impetus on a less than 3% duct leakage rate, and a system airflow rate to be within 10% of the design, both supply and the exhaust streams. The entire system has to be complete before air sealing can begin, and this usually coincides with sheetrock activities. So that means we have to kind of coordinate with the carpenter for leave outs, because as you can see in the picture below, yeah, okay, you went to that slide, sorry. You need some space to do the run out for the discharge of the AeroSeal unit, and you need to have a cutout in the riser to inject the air seal. And basically all it is you're sealing the interior ductwork with an aerosolized emulsion of water, and it's a vinyl acetate polymer, and the polymers stick to irregularities in the ductwork, like holes, and it fills it in slowly. And as they're doing this process, they're taking real-time measurements of the leakage or the pressurization in the ductwork, and they can tell when they've hit the threshold and when to stop doing the air sealing, because the threshold is basically your leakage rate. The preparation is really crucial for the air sealing process. You have to make sure you isolate all of your motorized dampers, any dampers really, any fire dampers, fire smoke dampers, motorized dampers, car dampers, because obviously this stuff is going to coat it, and it's going to make it, it's going to affect its functionality. And then at the air outlets themselves, it's really important that those air outlets in the apartments, for example, they're blocked up and sealed, and that the car damper is removed. And one more important thing with meeting those flow rates is actually using these constant air regulators. Basically, with a manual damper, you're going through and you're making adjustments, and it's a lot of work to make manual adjustments everywhere, and go back and forth and try to make the flow rates be within 10% of your design flow. And then also, you have to prove this to commissioning as well. And the car damper is great because it acts within a prescribed range and meets a set flow. And they even have car dampers now where you can basically tighten or loosen the baffle in it to allow or to permit or restrict airflow. So even if your car damper isn't providing the right airflow rate, you can still make minor adjustments to get it to make the right CFM. On the next slide, this is an example of a field condition where the electrician couldn't get anything in the deck. It wasn't feasible for his conduits to an exterior electrical closet, so we had to go from our interior space to our exterior space, and you can see there's quite a bit of conduit that's coming through here. And basically what we did is we utilize existing materials and we utilize approved materials and existing materials on the site to basically seal this penetration. The extruded polystyrene and then the spray foam, and then we softened it over this whole condition to basically give one big insulated chunk to isolate those conduits as best as best as we could, because they're obviously acting as thermal bridges. And then lastly, the most important thing really with the whole passive house thing is getting everybody on board. We talked about it briefly, but quality control, getting everybody to buy in and buy into the details, going through trainings, reminding the contractor and really working hand in hand with them to buy into the process, because that's really the key to a successful passive house project.
And to add, and it's without a doubt that any project is always a collaborative effort, and every team member has to come together to make a success out of the project. All the consultants, architect, the main contractor, the GC or CM, subcontractors, everybody has to be committed. And even if one of these entities is not committed, the project could become very easily a lot more expensive and difficult to build. So I do want to say, I noticed that some of our colleagues on some of these passive house projects happen to be at this presentation today, and I do want to add special thanks to them. To name a few: Datner, Curtis and Ginsburg, Handel, Steve Winter. It's nice to see you all at this conference, and I know we've all presented together some. Obviously not right now, but I'd like to say thank you for helping us get these projects to the finish line, and fingers crossed, and hopefully we can continue saying that, we always finish all of our projects ahead of schedule.
Thank you so much for the presentation. Amy will take the questions from the chat, and I just wanted to ask probably the first one. What's the percentage of passive house work compared to the non-passive house projects? Do you have an estimate?
From Monadnock's end, at the moment we have 3 projects that are going for the passive house certification. 1 project being built for passive house, but not going for certification in a sense, built for passive house standards. So it's really 4 projects that are. I think 4 at a time is a considerable amount of projects that to have ongoing at any point. Percentage wise, it's not quite 50,
I'd say like 25, it's like 20-25%, Harapriya?
Probably, yes.
Very good. And I saw that you guys are the 5th largest contractor in New York City, so that makes quite a lot of passive house work coming from you guys, I assume.
Great. So the first comment from David Levine about the architects, and Haripriya just kind of named everybody. I think you named everybody that you've worked on with these projects. And then the next one is from Jay Murdoch. What is the material of the thermal block on 4-inch thermal bridge free? I think, yeah, he's just looking for the name of the material that the supportive thermal blocks that you guys use.
Yeah, the thermal blocks are made from a company called General Plastics. They come out of Virginia. The manufacturer, I believe, is CSI, and it's basically a high strength, high strength polystyrene foam, like a blend.
There are alternative manufacturers like Fabrica. It's just generally we've found CSI of Virginia to be relatively more cost effective. They work with us in customizing like all the prefab penetrations, getting it to the sizes that we need, lead times. It's generally worked better for us in the projects. But there are other products we've used too, like Fabrica, for example. That particular photo we were referencing had the thermal block, as Joe mentioned. CSI of Virginia thermal block.
Great, thank you. And then where and why is the blower test criteria for multi-unit buildings to pick only adjacent?
So and just to clarify, I was referring to the guarded blower door test. Maybe this was just a miscommunication. Obviously, the final blower door is for the entire building, and no element is being left out of the test. The guarded blower door, it's really up to who is doing the test to identify how much you want to test in that. You could test 8 floors, you could test 8 apartments. It's a question of the extent of what you're testing, and you don't have to test an entire floor. You could pick and choose 2 or 3 apartments, and then you would just be including the apartments adjacent to those, because in a sense you would have to pressurize the whole system to imitate it. So that's what I was referring to.
And to add to Harapriya, sometimes it's not always guarded blower door testing. Sometimes we do localized testing of exterior walls with a job built testing encapsulation that we build on site with we depressurize it. We use smoke sticks. Sometimes we test windows. So it's not only the guarded blower door test too. We use other ones as well.
So which spacer bars do you usually plan for these triple glazed windows? I see that Jose actually provided an answer as a window rep.
Yeah,
Jose,
we've seen different spacers depending on who the window manufacturer is. There's different spaces depending on who the storefront manufacturer is, and you could customize it, if meaning change the spacer. And obviously, warm edge spaces are the preferred option for passive house projects. And we've seen plastic. There's silicone, not that very preferred. Polyamide spacers generally used in the storefront systems. So it's varying. And I did see, yeah, one response. I'll let you complete that.
No, actually, she did a good job. So that's exactly right. Just make sure that the spacers are made out of any type of metal. You want to have some composite material, a good desiccant inside.
next question, can you address the issue of installing the windows in line with the exterior and primary insulation to keep the thermal flow line straight? Detailing that has been a challenge in my experience. And
first of all, I want to say hello to Gal. Hi, Gal. I am working with Gal on a project right now, non-passive house though. I do agree that getting the windows in the insulation layer is a bit of a challenge, but it's not quite impossible. It's more of a constructability item. We do have, and also a design item, I should say, because sometimes the look of having that recess where the panel or the brick return is to the window is desired by the architects. Another element to consider is just a sequence of construction. If you have masonry work going on above, the windows are installed, and if the window is proud, you can't really install the windows ahead of the masonry work. You have to protect it from falling debris. And in general, based on the performance mock-up testing that we've done, we've found the windows that are basically in line with the slab edge, if you want to call it that, with the CMU to be having, if I want to call it idiot proof, to be airtight and good sealing detail with the caulking.
From Steve Mann, for rooftop ERVs, do you have height limitations, restrictions due to the stack effect, etc.?
I do want to take this question. Tommy may have more to add. We're contractors, we're not engineers. So this is a question we've actually been asked at other passive house conferences too. And to be honest, I don't know what the real discussion is and what the answer is at the end of that discussion. One thing we can say is that from the Cornell Tech project, and maybe Tommy can add after me, from actual observed results, that there is no negatives from stack effect that have been witnessed at that project. Again, we're not consultants, so I don't think we're qualified to answer this question.
Yeah, I mean, I don't want to dive too much into it as well, but obviously, yeah, like that's a 26-story building, and we have risers going from 26 all the way down to the third floor in that building, and there was no issue with balancing, and there was no issue with meeting the criteria from the design team.
Skipping down to Valerie, did you experience any issues or complications while going through the permitting process?
Short answer, no, because I don't really think there's anything different with passive house projects and permitting in any way. One thing that comes to mind is the CCD one that Tommy briefly touched on for unitized ERVs, that there is a mechanical code requirement to be a minimum of 10 feet away from any intake for an exhaust. And if you were to go with a unitized ERV system, it's hard to meet that requirement floor to floor. Sometimes even if you're alternating the supply and exhaust on the different floors. So in cases like that, you may have to get a CCD one approved from the city, allowing less than 10-foot requirement. We have had this happen on the Morris 2 project, for example. I can't really, off the top of my head, think of anything that would affect the permitting process otherwise.
And then from Jay Murdoch, for the MEP and the Cornell project, what did you learn for the design and execution, and how did this inform how you'd approach a similar project in the future, and why? And then I see that Alex started to apply that as well.
And just to quickly introduce Alex to everybody, he was the lead from Monadnock on that project. He's the vice president of the company. And Tommy, you can continue.
No, I mean, yes, I would echo exactly what Alex said, though. And Alex, if you want to go, that's fine.
Sounds like Alex is on mute.
Okay. So anyway, basically what Alex is saying, and I do think that's the biggest takeaway is actually this distribution for the VRF is the horizontal is difficult to work around the perimeter. Ideally, regardless of the system, a vertical distribution is I feel we feel the better installation and better quality QA/QC wise. Like I said, you're not dealing with that horizontal penetration condition on every floor, and then dealing with mobilizing a contractor to every floor to get these systems started up. You know, instead of having everything on the roof in one place, coming up in one spot, it really simplifies the installation. And like I said, the QA/QC.
Tom, why not depend on air sealing ducts from the exterior rather than deal with the headaches of aerosol? I think Alex might have weighed in on that as well.
Yeah, I mentioned it. I mentioned down below. I responded very late to that, but basically another consideration you have to make is the AeroSeal process needs temperatures above 40 degrees, and sometimes depending on where you are in construction, you don't have the ability to go up on the roof and AeroSeal from the roof. So, you know, we don't plan to AeroSeal from the roof because of that. You know, you can't control environmental conditions, but you can kind of control that condition in an enclosed space. So yes, it is feasible. It is feasible to do it from the roof. And, you know, if the conditions were right, that's what I would do, but you have to plan for AeroSealing from the floor below.
Tom, I don't know if this question is maybe more for just duct mastic type of sealing that you would typically do on every project versus AeroSeal. I think that may be more the question. I don't know what the question is, but I'm guessing.
Right. I think it's, you know, you're getting kind of 2 for 1 with the AeroSealing process, right? You're doing your duct leakage test at the same time that you're sealing your ductwork and making sure that all of those whatever gaps there could be are sealed. And at the time that we AeroSeal, we've already gone ahead and sheetrocked and closed in all of the duct risers all the way up to that last floor. So if we had to do the air sealing, if we had to do a pressurization test, we would have to basically leave out the sheetrock until we had all the ductwork up to do our leakage test or stage our leakage test, and that would just become really cumbersome. And I just feel for the money, the AeroSeal process is worth it. It makes it straightforward and no headaches. I don't know if I really answered that enough, but
so if you don't mind me just throwing in, so at what point do you want to AeroSeal then? At what point in the project?
Once the whole system is up and connected, that's when you AeroSeal.
Okay. And you're saying that because, you know, you might have already sheetrocked certain areas, so it's
right. You're gonna be put. I mean, you can't hold up the whole job for a leakage test. You can stage your leakage test, but again, that's going to be probably more expensive to the contractor than doing an air sealing.
And you may not be air sealing on every job if you don't have vertical risers. It's really doesn't pay off. It's really when it's makes sense for the project, what conditions it makes sense for the project. But for typically when you have vertical stacks, from a cost perspective, it pays off to AeroSeal versus deal with the headaches later.
Great. That's helpful. Thank you.
And Amy, just to add for Metcalf, just to give you an idea, it took 3 weeks to AeroSealing all the mechanical systems at the Metcalf project. We just finished about a month ago.
Great.
And actually, even at Cornell, Joe, I don't know Metcalf as well. Like at Cornell, it was even shorter than that. The riser, the layout was pretty simple, and it's really only a few days that he needs. You know, we had over 40 risers at Cornell, and it was really, he was on site less than 2 weeks for our project. Yep.
Jane Sanders says this was a great presentation. Will the video be available afterwards? Yes, Andreas, we're recording it, and I believe we can find it on the NYPH website. Is that correct, Andreas?
We'll send it out tonight, and it's going to be available on the website as well.
From Sarah, she says, are you able to apply some thermal breaks and improvements to air sealing specifically on other non-passive house projects? Are you having conversations with those owners, developers, architects on non-passive house projects during pre-construction to apply lessons learned to improve those projects' energy and durability performance? Great question.
The answer for that is yes. I'm actually working on a non-passive house project right now. My next project that I'm going to be working on happens to be also non-passive house, but I can tell you that the details are, and actually Datner is on one of those projects also. And I can tell you that a lot of the principles from passive housing, that maybe just our experience being on those projects, now you're kind of buying into it, and you want to give the developer a better building, and we are implementing a lot of the details that are not significantly driving the cost of the project up. And to be honest, the energy code has also had a lot of changes since the first passive house that we built, which was Cornell Tech at this point 6 years ago. So the energy code, especially now the new code that's coming out, it's already meeting a lot of the previously passive house only requirements in the energy code. So yes, there are non-passive house projects where most of the details that get applied, probably not all, and it all comes down to what is more cost efficient for the value of, I guess, the return value that you get out of that detail.
What's the trend on shift to passive house versus other low load buildings, say other that passed in the past 3 years? It was stated that about 25% are passive house now, but where do you see it in 3 to 5 years, and why?
This one may be a hard question to answer, because 3 years ago we had one passive house at a time. 6 years ago it was one passive house at a time, and now we have 4 projects that we're working on. So I do see a lot more projects going for the certification, possibly, and even if not certification, building to passive house standards, because the details make sense. And the new energy code, like I said, I think is going to make it even more easier to be able to meet the requirements. A matter of getting certification, that's an developer's decision. But I do think that a lot of at least the principles of passive house are going to be seen in majority of the construction projects in the next few years.
What do you think needs to be improved in terms of oversight from DOB on the air sealing to ensure other projects can meet the same passive house air tightness? TR8 or special inspection changes?
DOB already has TR8 requirements where it's not so much in terms of testing, I should say, but there are requirements that there's pre-tested, standard test reports. Like, for example, the AVB that you're using should be meeting the Air Vapor Barrier Association requirements for air leakage, I guess, requirements. So in my opinion, DOB in a sense is already having the oversight on this through the special inspector and the energy code requirements that are specified on the drawing. And then a lot of the air sealing has to do with water penetrations also. So, yes. And you are inspecting that with your special inspectors in the field.
Yeah, the control inspector for the TR8 is looking at the application in the field, so they would be witnessing and verifying it's material that's approved by the architect.
Again, I think this is tied into how the codes are changing, because as the codes get more stringent, than those inspections do as well. But they've already gotten much more stringent than they were in like 5 to 8 years ago. So we've already seen a lot of changes there, I think.
So thanks, Amy, for doing the Q&A, and thanks for Monadnock and the team to present. We will hopefully organize many more. I think there's a big need for constructability of passive houses. I think that's certainly a hot topic. So thanks for the presentation, and we look forward to many more. Thanks, guys.
Thank you, everybody.
Thank you, everybody.
Thank you.